I have disconnected. Were you able to see my presentation?
No, sir.
Sir.
Okay. Okay, I will start from the beginning. Okay, I hope it is visible now. The slide is visible now, I hope.
Yes, sir.
So as I was discussing that, yes. So as I was discussing that, for a cantilever beam, where fixed and another, we know that the bending moment, nature of the bending moment is developed at the fixed end and the end. So, and also if you see the deflected shape of the cantilever beam, then you can find that the tension is developed at the top face, top end of the fiber, and compression is developed at the bottom end of the fiber, which is just of a simply supported beam. So we have to main tensile reinforcement should be at the tension face, means at the top face. Okay, unlike your simply supported beam. And to follow the design, we have to make some consider some important points while designing. We have to keep in mind that the main tensile reinforcement is to be placed in the tension zone. Okay, and that should be above neutral axis. So the main reinforcement, so the main tensile reinforcement should be above neutral axis, because below the neutral axis there will be there is no point of giving tension at tensile reinforcement at the compression zone. Next point is that the depth of the beam can be varied. Why? Because we know that the bending moment is varying with the span. So we can have a larger maximum depth at the fixed end, and we can reduce gradually up to the free end. But the minimum depth of the beam should be kept as 150 mm for the free end. It should not be less than that. Next point is that the see the design of the cantilever beam. If you have to consider the curtailment, as discussed in previous class, that we can provide the curtailment up to 50% of the main bar, 50% of the total reinforcement, and the distance of this curtailment that we provide should be half of the span, half of the effective, the development length, whichever is greater. Okay, so this is the condition for curtailment as already discussed in previous class. And we have to also make sure check for the deflection, maximum deflection of the beam, and that is it can be found out from the L/D ratio. So that is depth, effective depth. So for cantilever, anyone if you remember, control for controlling the deflection maximum, the ratio should be for simply Supported bevel, it should be how much? Control for controlling the span by effective depth. It should be 7. And I have also shown how to get the modification factor from the percentage of tension reinforcement plot. Okay, that we will see. So let me discuss about the design of cantilever beam with an example. Value also includes its self weight, so no need to calculate self weight otherwise. And grade of concrete is M20, steel is Fe415. So from here we can get the 3 meter FCK 20 Newton per millimeter square M20, Fy 415 Newton per millimeter square, and W is 14 kilonewton per meter. So first we have to calculate the factored moment. Okay, and this factored moment and factored shear force, we have to get it by multiplying with the factor of safety. Okay, 1.5. So design load is 21 kilonewton per meter. So we will get the ultimate moment. Okay, mu is W into L square by 2. So from here we'll get the value of factored moment, and shear force is W into L. So value of Vu is also obtained. Now we know that for deflection criteria, the value of L by D should be 7. So considering this, we can take our effective depth of the beam as span by 7. So 428 millimeter we can consider. Okay. Now let us assume that the overall depth of the beam, we have to assume it, and we have to check the cross section of the section of the beam that we have considered, and we have to also check the quantity of reinforcement that we will going to calculate, and check it for the minimum criteria, minimum provided criteria. So considering by assuming the overall depth D as 450, and this 450 is the depth at the fixed end, and we know that we are actually varying the depth. So the minimum depth is considered at the free end is 150 mm. So considering it, we will get the value of, we'll consider the value of clear cover as 20 mm, dia of the is 8 mm, in bar as 16 mm. Okay, so considering all this value, this is a trial and error procedure, all of you know. Will proceed it. Okay, so the width of the beam is considered as 250. So depth from overall depth, we can get the effective depth from the calculation I have already discussed. How to get the effective depth from the overall depth by subtracting the value of clear cover and stirrup. we have to calculate the minimum depth required. Okay, so minimum depth required formula, it is root over of mu by ru by b. So for that we have to know the value of ru. The value of ru, as you know, is from the equation 0.36 1 minus. So by we all the values are known. So how will you get the value of xu by d? We know from the table that the value of xu by d for Fe415 steel is 0.48. So putting those values, and you will get the value of ru, and putting all the values, you will get the value of d required. So here the value of d required comes out to be 470, okay, which is less than 414 mm. So the value that is considered from here is okay. So we can proceed with the depth, minimum depth that is required, that we have got from our assumption. We have to calculate the area of tensile steel. Okay, so to calculate the area of tensile steel, we know the formula that mu is equal to 0.87 Fy into Ast into d multiplied by 1 minus Fy Ast by Bd Fck. So all the values are known except Ast. So from this equation, uh, we will find the value of Ast. Okay. So after obtaining the value of Ast, next step is we have to find the minimum area of steel. So the minimum area of steel is obtained by the equation As is equal to 0.85 Bd by Fy. Okay, so all these formulas are actually given in your IS code, but I will suggest you to by heart all those formula. It will be required for easily you can solve any question whenever it is asked in the exam. So minimum area of steel from here we can obtain, that is 211 mm square. It is obtained, much lesser than 742 mm. So we can provide this steel AST, and since we have used 16 mm main bar, so converting it into area, and we can obtain the number of bars that are required from dividing the whole amount of area of steel AST divided by area of each bar. So we can obtain that is almost 4, around 4. So we can provide four numbers of 16 mm bar. Okay, okay, I hope no problem with this. So this so next step is to find the curtailment of bar. Okay, so to find the curtailment of bar, we know that the criteria is that the span should be minimum half of the effective span. That span, and we can obtain the value of tau bd, that is the design bond strength. So from this table, okay, so from IS code this clause 26.2.1, we will obtain the respective value of permissible bond stress for the value of tau bd from the given criteria. Here we have M20 grade of concrete, and for deformed bar, that is Fe415, the value is 1.92. So considering this value 1.92, for M20 and a deformed bar, okay. So minimum, just a minute. I think one is missing.